Looks like I've got your submissions from homework 10. The exam is on Tuesday, and for that, what have we been doing for equation sheets on the midterm? You made your own, right? Okay, so you can make an equation sheet, and did I give you a packet, like the FE packet? Bring that along as well. The final exam, we have 2 hours for that, and so it'll probably be a little bit more lengthy than the midterm exam was. It'll have both of the same components, a conceptual component that's mostly short answer, and then problem solving with added emphasis on the material that we've covered since the midterm exam. Now, there will be a computer part on it, and so you can expect that you might get either a WaterCAD problem or a HEC 1 problem with WMS, or possibly both. So I don't think any of you will mind that, because it seems like you're all getting along pretty well in both StormCAD, not WaterCAD, StormCAD and WMS. So if you want to bring your own laptop for that, do. Otherwise, the tablets will be available. Evan?
The paper for the exam, can we write just on the front or on the front?
Front and back. One paper, front and back.
And you said WMS is a possibility as well.
It's a likelihood. It's more than just a possibility. It's a bright and shining likelihood.
I'm just going to make sure I have 9.1 because the computers are unstable.
I probably won't ask you to go from outlet location defined with lat long all the way to a full model. I'd probably either start somewhere in the process and have you finish it, or ask you to go partway through the process, and so. But it would pay to familiarize yourself with the workflow, and so. Any other questions related to the final exam, not the midterm, final exam? This is class 28, and we only have 28 classes, so this is it. This is the end. We're talking about water today, and is there a slide there? All right. Did I skip over this one? I had that. Oh, it's just animated. That's what it is. I'm so confused because I knew I had a photo on my first slide, but there it is. What we're going to be talking about today is water underneath the Earth's surface, and we've already talked about that a little bit when it came to infiltration. But really, in infiltration, what we were mostly concerned with is how quickly is water going from the surface into the subsurface. And we didn't get into a lot of detail about how it moves side to side, or at what rate can it be pumped out, or how does the water surface underneath the ground vary? The level of the aquifer, how does that vary when pumping occurs? And those are some of the big questions that are within groundwater hydrology. And it's important because not only is a lot of agriculture and drinking water supplied with underground aquifers, but a lot of those underground aquifers have been contaminated over the years with pollution. Like chlorinated solvents that have their origin as cleaners, like engine degreasers, or dry cleaning fluids that were discarded before modern environmental regulations were in place. But also a lot of contamination has occurred from leaky underground storage tanks, and that has an acronym, LUST. Leaky underground storage tank. So LUST has a new meaning now. That's truly what LUST is when you're talking about environmental contamination. It's a leaky underground storage tank. So it's important to know how water moves underground so that, number one, you can predict the quantity of available water, but number two, so that you can understand how pollutants may be transported through the environment. If you have an industrial area some ways from a residential area that has groundwater as its drinking source, then you need to know how quickly a plume of contamination might possibly move towards that drinking water source. So those are some of the questions that are asked in underground subsurface hydrology, and the image there is just representing that there are a variety of computer tools that have been developed to help aid in the analysis of water movement in the same way that there are tools for surface hydrology. Aquaveo, whose WMS product you've used this semester, has two other programs that are sort of their big flagship programs. We've been using Watershed Modeling System, They also have something called Surface Modeling System, SMS, and that's mostly about flow in rivers. It helps to set up HEC-RAS models, which is solving water surface profiles and gradually varying flow type scenarios. But then they also have a program called GMS, and that's Groundwater Modeling System. And that breaks the underground environment up into a mesh, as sort of a grid, and it uses computational analysis to predict how water will flow through that grid. Groundwater is important partly because there's so much of it. I guess, depending on the way you look at it. When I said there's so much groundwater, there's not that much when you compare it to how much of the water is tied up in the oceans and frozen in ice caps and glaciers. If you look at all of the H2O on planet Earth, the vast majority of it is in the oceans. But if you're considering the fresh water that humans can actually get at, there's a lot more of it as groundwater than freshwater lakes or rivers. 0.3% of the available water on Earth is less than a kilometer down from the surface. And they break that up into two different groups because typically the water that's deeper than 1 kilometer wouldn't be economical to pump up to the surface. And in fact, most groundwater wells would be far less than 100 meters in depth. And so 1,000 meters is certainly a stretch. But there's a lot more of it, 0.3% compared to freshwater lakes, which is 0.009%. And so there's a couple of orders of magnitude in the difference of water that's available. So groundwater is an important resource in a lot of the United States for agriculture, and unfortunately there are some communities that are terribly threatened by the reduction in available groundwater. The water tables have been falling for a number of years, and El Paso, Texas is one that's sort of notorious for its rapidly dwindling water supplies. Here are some key terms that you should commit to memory and hopefully, more than that, actually understand. An aquifer is any geologic formation where water can be withdrawn in significant amounts, and it can be comprised of any kind of underground material, whether it be sand, gravel, fractured rocks, soil. An aquifer is just a place where water is inside of the voids. An aquiclude is a confining layer that sort of slows down the transmission of water. It has water, like for example clay has water, but the hydraulic conductivity of clay is so low that it sort of acts as a barrier. And an aquefuge, by contrast, doesn't have water and it doesn't transmit it. And so this hashed-in layer here could be either an aquiclude or an aquefuge, but what it does is it has the effect of making a barrier between the confined aquifer and the unconfined aquifer. You can tell here that the unconfined aquifer has sort of a clear path to the surface. Water that falls at the surface can infiltrate down through the pores and make its way into the confined aquifer, and this confined aquifer is perched on top of the confining layer. But the confined aquifer is sandwiched between two confining layers, and this is just a 2D representation. We're not considering how there might be variations if we go into the page here. But the confined aquifer is actually under pressure, and you can see from the piezometer that the water surface will rise fairly high because of the pressure here. And what you need to ask is, why is it pressurized? Why is it that the pressure here is high enough that water can actually spurt out of a well that's dug? And the reason why is that the recharge is occurring high on a hill, and here you can see the water surface is very high, and so this is sort of acting as a tank. Essentially, the confining layer is a little bit like the walls of a tank. And you can think of this section of the confined aquifer that tapers off sideways as a pipe. And so if there's water in a tank and you put in a piezometer here, the water level is going to rise not quite as high as the original water elevation in the tank. There's going to be some elevation difference there, and that elevation difference is a function of the energy loss between 2 points. And you can see here that the water level in these piezometers is lower than the original water depth in that recharge zone, because the water has to flow through a media as it makes its way through the confining layer. The Artesian aquifer is an aquifer that water will come all the way up to the surface. And this is illustrating an Artesian aquifer. There's enough pressure inside the confined aquifer that the water will flow all the way up to the ground surface in that case. Another word for the confining layer, something that slows down the transmission of flow, is an aquitard. That reduces the overall hydraulic conductivity of water movement through the aquifer. Now, we've talked about an unconfined aquifer and a confined aquifer, but sometimes one of the confining aquifers, if this was rock, for example, and it was fractured, there may be leaks through the confining layer. Or if it was just a very thin layer of clay, it's possible that water could move through that clay more quickly than if it was a thick layer of clay. And so when you have a confined aquifer but water is seeping through there in appreciable amounts, that would be classified as a leaky aquifer. And so you can have a leaky confined aquifer or a leaky unconfined aquifer. So for example, if this, forget about the confined aquifer underneath. What if you just had a layer of clay and an unconfined aquifer above it? It's possible that if there was a very thin layer of clay, or if there were discontinuities, or if this is rock that was fractured, water could be dripping downward into the layers below if this unconfined layer was perched on top of a confining layer. Or it's possible that there can be a leaky confined aquifer and the water may be leaking upwards. If it's under pressure, it could be leaking upwards and downwards, potentially. And so depending on the pressure inside the confined aquifer, if it's leaking, it could leak both directions. Now, we've talked about Darcy's Law already this semester, and this illustration shows that as water flows through a column of soil, that the pressure of water in the inlet is higher than the pressure of water at the outlet. And that delta H, the difference in piezometric pressure, is related to how much energy loss occurs as it flows through that porous media. And so we can use this expression of measuring the change in elevation of the water surface at the inlet and the outlet, the length of the column, L, and the hydraulic conductivity, K, to find out and estimate what the flow rate through that column will be. And so if you have a large area, you'll have a larger flow rate through a column of soil, because area is one of the parameters in Darcy's Law. And the key here is classifying the hydraulic conductivity of different soils and media. And when you want to know how a well is going to perform, you go out into the field and can classify the K value of the soil. And that's one of the important parameters that tells you how productive a groundwater production well might be, or how quickly pollution can move through the underground towards a well. Now, this is showing two different scenarios in this image here. It's showing the before and the after simultaneously. So there's a well here, and before you turn on the well, the water surface is flat. Now here's the ground surface up above, but the aquifer will have a flat water table before the well is turned on. But once the well begins to discharge, there's something that's called drawdown. And that drawdown sometimes has another name called a cone of depression. Now that's kind of a funny phrase if you think about it. You know, it's getting into the winter and you're gloomy because the semester is ending, so maybe we're all entering a cone of depression. But here it's talking about a physical cone of depression that is the water surface is lower close to the well casing. Now you can see here there's this hash marks here, a grid. And what that represents is that this pipe that goes down into the soil is slotted. They call that a screened well. They don't want dirt to get into the well. They only want water to seep in. And so there's a fine mesh that allows water to enter the well, but keeps the soil out. There's an impeller down here inside the well casing that's forcing water upward, and this center shaft is like a steel metal piece that's connected to a motor at the top of the shaft that's spinning the impeller. So water is pumped up through the pipe and out into some sort of a receiving works, but the effect on the groundwater is that water is flowing sideways towards this well. And we're just looking at it in cross-section, but it's a circular thing. It's a cone, sort of like a funnel that you'd use to fill up a flask or something. So you can see that the more the water, if you increase the flow rate, then the cone of depression will get deeper and deeper and deeper. So if you have just a low flow rate, if you're hardly pumping any water out, then the cone of depression wouldn't be very dramatic. But the more you pump, the drawdown increases. Now, this can be a steady state thing. It's not like when you're pumping, the drawdown gets worse and worse and worse and worse until finally it's all gone. It draws down until it reaches an equilibrium, because it's this drawdown near the well casing that's actually sucking water towards the well. You can see it's talking about a radius of influence, and the radius of influence is how far you have to go away from the well to where the drawdown begins. It's flat, but then it starts to have a reduction in the elevation of the groundwater surface. That's the radius of influence for a certain flow rate. So a low flow rate would have a small radius of influence. A high flow rate will have a much larger radius of influence. But when you reach equilibrium, the drawdown sort of gets to its steady state location, and the water is continuing to gather towards the center of that well. And it's the drawdown that is sort of the driving force for the radial movement of the water. The water moves towards the well because there's less piezometric pressure at the well than away from the well. And you can think about that drawdown curve as what would happen if it was just a river. You know, if you had a river, even if it was flat, I've drawn it inclined just out of habit, but even if it was a flat river, perfectly flat, if you had water and then something was sucking the water away so that you had like a wall, of course the water is going to move towards the point where there's been a drawdown in the surface of it. And that's the same thing that's happening here. Water moves towards the well because of the drawdown. And so we're going to be solving equations that describe that cone of depression, how far it extends, how much drawdown there's been. You can see a comparison between sand and gravel. Now, why do you suppose that sand has more of a drawdown here than gravel does for the same flow rate? They're extracting the same flow rate from both wells, but what these two images is showing is there's more drawdown if your material is sand than if it's gravel. Okay, you're getting pretty close to it. You're talking about the time it takes for water to move. What do we know about the movement of water through sand versus gravel? It's faster through gravel. If we go back to Darcys Law, what would we say about the hydraulic conductivity of sand versus gravel? Which is going to have a higher hydraulic conductivity? A high hydraulic conductivity means the material is able to easily conduct water. So a big K gives you a big flow rate for the same, everything else being equal. So gravel versus sand, which is going to have the bigger K? Gravel. So a big K means water moves through it easily. Now Cameron's comment was that water flows through the gravel more quickly. So why is it that there's more drawdown for the sand than for the gravel? What is it about the drawdown? Head loss? In which one? In the gravel. Okay, that's a good way to say it as well. what you may need to think of it in terms of is the drawdown is sucking the water towards the well that's, out here. You need more of a driving force when it's the sand, because remember, water flows through the sand with more difficulty. And so the drawdown is that driving force. It's what's sucking the water towards the well. And so if the sand isn't as easy in terms of water movement as gravel, the gravel doesn't need to have much drawdown because water flows through gravel easily. There's those big voids. But sand has smaller voids, and so there has to be more drawdown. It's more of a driving force.
The area of the kind of depression about the same because gravel has a smaller drawdown with bigger radius and is that kind of the way?
They've actually, I'm glad you brought that up because they've been a little bit sloppy in their presentation. If you have, that's interesting. No, I don't think you could necessarily say that the area is the same. But that's an interesting question. We may have to set up a problem and explore that. But that isn't the for sure relationship. There is an equation that'll define radius of influence versus drawdown, but I don't know specifically that for a certain flow rate the integrated area is the same for both of them. If you have two wells together, they have an overlapping cone of depression that depresses the water elevation even further. And this is showing what the cone would be if only this is well A, this is well B. So if you were only pumping well A, this is what the cone of depression would look like, that top one. But because well B is also pumping, these two cones overlap and they're further down than they would be individually. So it's an additive effect, as you'd expect. The drawdown is combined. So here's some additional terminology that's used with subsurface hydrology. We have a fully penetrating well would be one that goes all the way through an aquifer. Okay, so here I'm going to draw a confining layer. This is rock. And then that's the ground surface. And here is a water surface, underground water surface. A well that is fully penetrating goes all the way down to the bottom. And then, here's my slots. It doesn't matter if the slots are all the way up. But the fully penetrating well, the well casing goes all the way down to the bottom of the aquifer because the aquifer is going to have some thickness. We're going to say that the thickness of this unconfined aquifer would be H. And in the case of a fully penetrating well, the casing goes all the way through the thickness. A screen, we've already talked about the screen, and its purpose is to keep sand out of the well but allow water to come in through filtering out the water. And the well radius is the actual, if you have the center line of the well, the radius of the well is what's the distance from the center line to the outside well casing. So if you have a pipe going down that's 0.5 meters in diameter, so if this was, boy, that marker is just about done. If this is, diameter is 0.5 meters, then of course the radius for that well would be 0.25 meters. And the radius is important because sometimes we can substitute the radius into the drawdown equation as one of our locations of interest. Yes?
Just make sure I'm clear. What exactly is the drawdown?
I mean the difference between where the water was before pumping began and after pumping begins. And so let's say that originally H was 10 meters before pumping starts here. And then I turn on my well and I start pumping water out. So what that's going to do is it's going to have the cone of depression kicking in. And so it used to be 10 meters here. Well, let's say that I go a certain distance over, that I go 15 meters away from the center line of the well, and now what I can measure there is that H is maybe 9 meters. And so the drawdown at a radius of 15 meters would be 1 meter, because it used to be 10 meters of thickness. Now because of the drawdown it's 9, so the drawdown is 1. I'm glad you asked that. That's a good question.
So you're always pulling water from the bottom of the well. The drawdown is just measured where the water level is.
Uh-huh.
You're pulling from the bottom of the well.
Yeah.
All the time.
Yeah. Mm-hmm. Transmissivity is the product of a well's hydraulic conductivity and the aquifer thickness. Aquifer thickness is H in an unconfined aquifer, or lowercase b in a confined aquifer. Hydraulic conductivity we talked about already. Aquifer thickness is the vertical distance that water can be flowing through. Transmissivity was defined on the last slide. Remember from previous courses that piezometric head is simply the pressure divided by the unit weight of the liquid plus the elevation, whatever your elevation above the datum is. Ordinarily, the datum, the vertical datum, will be taken as the bottom of the confining layer, so that your piezometric head would be the pressure of the water plus its elevation above the bottom of the aquifer. And effective porosity, we did talk about that when it came to infiltration, but remember that the porosity of any media can be greater than the effective porosity if the voids aren't connected. And so the classic example is lava rock, where it's a very porous material, but many of the voids aren't connected, and so it wouldn't be able to transmit water as effectively as something where it has the voids that are connected to each other. Here is the equation for a confined aquifer. This is the equation that allows you to find out how the piezometric pressure relationship affects the drawdown. And you can see that this lower equation is really what we'll use predominantly for problem solving. And what it allows you to find out, S is the variable that's assigned for drawdown, and you can see that S is measured as the difference between where the water elevation was and where the water elevation is after the pumping begins. And this is a confined aquifer, and so it's not actually the drawdown isn't a drawdown of the physical water surface, but it's a drawdown of the piezometric surface. The pressure is decreasing. So even though water inside this sandwich layer here, there's confining above and confining below, there's water all the way through this confined aquifer, but the pressure is decreasing because of drawdown effects. And so what this equation describes is the reduction in piezometric surface at some radius away from the center line of the well when you know the transmissivity. And remember that the transmissivity is the thickness of the layer, this B, the thickness of the confining layer, multiplied by the hydraulic conductivity. So let's put this into practice and get a feel for how the equations work. We have a hydraulic conductivity of 20 meters per day for this aquifer, and that's just a function of how easily it transmits water, and that's a pretty high hydraulic conductivity. So water is moving along in that aquifer. And initially, the piezometric surface before pumping begins is 14.53 meters above the lower confining layer. That's defining this H, the capital H that's shown. Before pumping begins, capital H is 14.53 meters, and the thickness of the aquifer is 6.6 meters. So B is 6.6. What we want to know is what flow rate should we take out? What is the Q sub W that's going to allow the piezometric surface to be 13.85 meters at a radius of 40 meters. So if you go 40 meters away from the center of the aquifer, the H is going to be 13.85, and then at a radius of 85 meters, the drawdown, or the the piezometric surface elevation will be 14.31. So we've got two different radiuses. We're going to have to calculate the drawdown based on the water elevations that we're given. And then we can put all of that into the equation and find out what's the flow rate that makes it happen. This question is essentially asking us to define the relationship between drawdown and flow rate. We have a confined aquifer and we are assuming that it's homogeneous, meaning that there's only one kind of soil in that confined aquifer. That's a big simplification because if you go underground, conditions vary. At my house, it's mostly clay and rock, more rock than clay. If I try to plant a tree, I have to chisel away at rock for hours and hours. But that's just an example of how this is a really kind of a broad simplification here. Maybe there are some places where if you go down, it's always the same soil, but that's one of the weaknesses of this method and why you have to go to a mesh method to really understand how water is moving underground, is that this method is assuming a heterogeneous soil. That's all of it is 20 meters per day. We have an aquifer thickness, B, of 6.6 meters, and H is 14.53 meters. First, we want to know the transmissivity of the aquifer, K times B. And the transmissivity is 20 meters per day times 6.6 meters as the aquifer thickness, and that's 132 meters squared per day. And that's an interesting units there, meters squared per day. That's like a flux. Okay, now S1 is talking about what is the drawdown at the well that's nearest our pumping well. And the way that we'd know how much drawdown is we'd put in like a monitoring well. So this is the production well. Where we're actually sucking water out of the aquifer. And then some distance away from the production well, we have monitoring wells. And we're not actually taking water out of these monitoring wells, but rather we just want to know, we'll use it to measure what is the water elevation. So there's going to be some drawdown. And at these monitoring wells, we're going to try and find out what is the drawdown here, S1, and what is the drawdown here, S2. So 1 is the location that's closer, and 2 is the location that's further away. That's really important. That's a convention that we have to honor based on the way the equation is set up. Otherwise, we'll get answers that don't make any sense. And S1, the drawdown at location 1, was 14.53, which is the initial water piezometric surface elevation. And then we know that when the production begins, the height of the water table there is 13.85 meters. And so these monitoring wells are essentially piezometers. Now here is the actual aquifer, and then we have confining layers. And we puncture the confining layers with the monitoring wells so we can find out how high does the water level rise to when we do that. And we find the drawdown at 1 is 0.68 meters. And the drawdown at 2, 14.53, was the initial elevation. The elevation after pumping begins is 14.31 meters. That's 0.22 meters. And this was for a radius of 40 meters at location 1 and a radius of 85 meters at location 2. Jonathan, why is there less drawdown at location 2 than at location 1? S is drawdown, so why is there less drawdown only 0.22 meters of drawdown over here, but 0.68 meters of drawdown at 1. Okay, because it's closer to the well. The slope. It's having to do with the slope of the water movement towards the well. Of course, water wouldn't be moving towards the well if there wasn't a decreasing slope. Water moves towards a location of lower energy. So it's higher, there's more energy at 2 than there is at 1, and there's even more energy at 1 than there is at the production well. So water flows downhill. We know that. And this drawdown curve is the downhill that water is flowing towards. So water moves towards the production well because of that curve. And so it makes sense for us that at radius 1, we've got 40 meters away from the production well. There's going to be more drawdown there because that's closer to the location where water's being sucked out. So everything makes sense so far. Let's just pop it into our equation here. If we have the equation that says T is Q divided by 2 pi S1 minus S2 multiplied by the logarithm of R2 minus R1. Okay, we can rearrange that to solve for the flow rate we'd like to know. That's going to be Q is 2 pi transmissivity, the difference in the drawdowns. You want to know what my favorite trick is for exams to see if students are keeping track of things? My favorite trick is to do what I'm doing in this problem, is to not tell you. Sometimes students mistake these elevations for drawdowns. Like, if you just said S1 is 13.85 and S2 is 14.31, that's the most common mistake that students make when they're doing problems like this, is to confuse the elevation of the water with the drawdown of the water. The most common mistake in these problems is students forget to do this step. They just immediately would substitute S1 and S2. They'd confuse the they'd confuse 13.85 instead of the 0.68 that's supposed to go in there. So this S is talking about the drawdown. So when we substitute in the values, 2 pi, the transmissivity we already calculated was 132 meters squared per day. Now the difference in the drawdowns was 0.68 meters at location 1 and 0.22 meters at location 2. And then in the denominator here we have the logarithm of 85 meters divided by 40 meters. All right, so put that into your calculators and see what sort of flow rate, what is the flow rate that we're going to get, and ask yourself, do the units make sense? Are the units that come out of that expression what we'd anticipate for flow rate? Okay, when you do the calculations, I hope you'll find that it is 506. Anybody else get 506? And the units here, if we have meters squared per day, which was what we have for transmissivity, and multiply it by meters, which is the units of drawdown. Now, this logarithm ratio here is unitless, that expression in the denominator, so it'll be cubic meters per day. So what we learned from this is that we've got a certain kind of soil here. The soil here is some soil that has a hydraulic conductivity of 20 meters per day. And we tested to find out what does the drawdown look like. We can do experimentation in the field to find out what the drawdown picture looks like. And once you're able to characterize the drawdown picture by measuring the drawdown some distance away from the production well and knowing what that distance is, you can put it into this well equation and find out what the flow rate capacity is. So, what's a reformulation of this problem? What's another kind of problem that you could use this stuff for? Well, what if you already knew the flow rate? So if Q was a given and transmissivity was a given, you might use this to predict what the drawdown will be at a certain location. Or you could say, how far out do I have to go? You could make the radius an unknown. You could say, I'd like to have these following two drawdowns. What will be the curvature of that piezometric surface? What will be the drawdown at a certain radius, or what is the radius in order to achieve a certain drawdown? Or even the hydraulic conductivity could be an unknown. If everything else was given, you could use a test like this to define what is the hydraulic conductivity of the aquifer. If that would be another way, instead of extracting a sample and putting it into the Darcys Law device, a column, and measuring with the two different static head reservoirs on either side, you could characterize the hydraulic conductivity of the reservoir by measuring the drawdowns, the radius, and the flow rate that's coming out. So it's a very, very useful expression. And this was for a confined aquifer, remember. Confined aquifer. Now, with an unconfined aquifer, there's a slightly different equation. We have to correct for the drawdown. There's something called a modified drawdown. And that just has to do with the fact that as the water begins to approach the well, that the surface of the water, here it's labeled as the phoratic surface, that means just the water surface. The water surface drawdown is a little bit greater than in prediction than it is in reality. So this modified drawdown is sort of the drawdown that you'd actually measure, S1, and then you have to take into account the thickness of the aquifer before pumping begins, H. And so it's a corrected thing. We'll do another example here, and I'm going to have you do this one from beginning to end. It's the similar kind of problem, except that we are going to say that drawdown 50 meters from the well is 1 meter, and drawdown 100 meters from the well is 0.5 meters. Remember that location 1, you know how there's a 1 and a 2? Location 1 is the location that's closer to the well, and location 2 is the one that has the greater radius, so further away from the center line of the well. We're given the saturated thickness, so here where you calculate transmissivity, instead of just the thickness of the confining layer, it would be the entire H that you had beforehand. All right, so see if you can find out, in this case, what is the hydraulic conductivity and the transmissivity of the aquifer. And of course, it's fine for you to consult with those sitting near you. All right, so the first thing that we really need to calculate is the modified drawdown at 1 and 2. And you can see that the modified drawdown is less than the actual physical drawdown. For the 1 meter drawdown location at 1, it turns out to 0.9792 meters of modified drawdown. At 2, it's 0.4948 meters is the modified drawdown. So when we substitute in the modified drawdown, the given flow rate, 0.4 cubic meters per second, turns into 34,560 cubic meters per day. Then we can find that the transmissivity is 7870 meters squared per day. And of course, the definition of transmissivity is the hydraulic conductivity multiplied by the aquifer thickness. So we can rearrange that for K, the hydraulic conductivity, and find it's 328 meters per day. So that's a very high hydraulic conductivity here, and it gives us an idea of how to do the calculations if it is a unconfined aquifer. The two approaches are, the same, it's just this addition of the modified drawdown step. Any questions from that example? Well, just to give you an idea of where things would head from here in a subsurface hydrology course, consider the case of two ponds that are next to each other. And there's a situation like that along Route 60 before Kmart on the right side of the road. You know, there's a cemetery on the right side of the road. If you're going past, it's actually before the, after the Prestera Center that's on the right side of the road. As you're going up the hill, and Kmart's on the right, Advance Auto is on the left. Anyways, there's a cemetery on the right side of the road, and at that cemetery they've got a very steep hill with a couple of ponds on that steep hill. There's a hill, and there's a pond, and then a hill goes down, and here's a pond, and it continues. And so you've got a pond here and a pond here. And the question is, what is, if this is, here's our water surface, and here's the water surface, free surface of water. What does the groundwater look like? How do you connect? This is an extreme elevation here. The type of problem that this is illustrating is, how do you find out what the shape of the groundwater surface looks like in the soil where you're connecting either two lakes, or maybe it'd be two streams that are under the influence of each other, because you've got a high water surface over on one side, low on the other. And these equations illustrate how you'd be able to define the shape of the curve if you've got two different hydraulic conductivities, K1 and K2. And we won't have enough time to actually go through the example of calculating what the water surface looks like through a porous medium like that, but I just wanted to give you a sense for such problems exist in the world, and there are equations to describe how quickly water moves between two different rivers. Knowing what the surface, being able to characterize this surface, really the point of it is in order to calculate how quickly water moves between the two water elevations. And so how quickly is water going from the upper pond to the lower pond is the kind of problem that this could solve. Well, we've got 10 more seconds left in the semester. I'll just say I've enjoyed the class a lot. I'm grateful that you took it. It's an elective that really doesn't satisfy any sort of design requirements, so you had no incentive to take it other than to learn, and I appreciate that. It's been a great semester. The final exam, remember, is on Tuesday, so if you have any questions on anything as you're preparing for that exam, let me know. I'm going to have this assignment graded as quickly as I can, and I'll put the scored assignments out in my box that's by my office door. So that's it for today. Please remember to plug in the tablet computers on your way out.